So we're going to begin homework number 7 here with some of our algebraic problems. Up first here we have one where we have 3 boxes being pushed to the right. We're asked a number of questions about this. The first thing I'm going to do is I'm going to draw a free body diagram showing the forces acting on each box, especially because that first question asks us to consider all the horizontal forces. We'll start by identifying what those forces are. So I started with all my vertical forces actually. I know that each of them has a normal force acting up on it and a force of gravity acting down. I call them FNA, FNB, and FNC, and then FGA, FGB, FGC. All right, so each of them has that. The reason why I call them different things is they have different masses, so the values for those will be different. Let's now think some about the horizontal forces acting on it. So I have this pushing force, which is acting on box A, going to the right, so I'll call that F. A then pushes on B, which means I have the force of A on B acting on box B, and also the force of B back on A acting on box A. And then I'm going to have the same thing with B on C. So B pushes on C, and that means that C pushes back on B. So I'm going to go ahead now and rank these forces from least to greatest. And I'm actually going to think a little bit about the idea of a system when I'm doing this. And here's why I say that. If I think about C as my system, what force is accelerating C? Well, that's just being accelerated by the force of B on C. All right, so that force is only accelerating box C. However, if I think about B and C as a system, they're being accelerated by the force of A on B. Okay, that ultimately is accelerating that BC system. Both of them, if we treat them as a system, are being accelerated by A on B. And if we treat the whole thing as a system, that's all being accelerated by F. Okay, so if I think about each of these systems here, all 3 blocks, both B and C, and just C, and I write my F equals MA for each. Let's take a look at what that is. And this is made a little bit easier by the fact that it's all on a frictionless surface. But if I'm thinking about all 3, okay, it's going to be F is equal to the total mass, M plus 2M plus 1.5 M, which is 4.5 M times A. If I'm thinking about just B and C, okay, I have the force of A on B, and that's going to be equal to the mass of these two only, so 3.5 M times A. And if I think about just block C, I can say that F of B on C is equal to 1.5 M, just the mass of C, times A. So that means that this is the biggest force, that's the second biggest, and that's the third biggest of those 3 forces. So the smallest force here is going to be F of B on C. That's going to be less than F of A on B, which will be less than F. One thing I do need to keep in mind, though, is F of B on C and F of C on B are a third law pair here, so they are equal. So that means that F of B on C, which is equal to F of C on B, both of them will be less than F of A on B. And we have another third law pair between F of A on B and F of B on A. Those are also equal. And so we can say F of A on B, which is equal to F of B on A. Both of those will be less than F, but greater than the B on C, C on B pair. All right, I'm going to clear up a little bit of space here and move on to part B. Now we want to rank the net force acting on each block from least to greatest. All right, so in order to do that, thinking about net force, that's another way of thinking about the sum of the forces. And the key there is going to be more mass equals more net force. Okay, all 3 of these boxes are accelerating at the same rate. So the one with the greatest mass is going to have the greatest net force. The one with the least mass is going to have the least net force. So that means that the net force, or the sum of the forces on A, is less than the net force acting on C, which is less than the net force acting on B. And that's just because net force is proportional to the mass. All right, so the more mass we have, the more net force we have. Moving on to part C, we want to derive an expression for the acceleration of the system. So I'm going to go ahead and treat this as a system here. That's going to make my life a lot easier. So if I think about the A, B, C system, the only force I have horizontally acting on it is that force pushing it. I also have Fn and Fg, but the only horizontal force I have acting on it is that force F. So when I do the sum of my forces equals ma, the only force there is F. That's equal to 4.5 m, okay, and that just comes from the total mass, so m plus 1.5 m plus 2m, adding up the masses of each of those individual objects. And so I end up getting 4.5 m times my acceleration. So when I solve for my acceleration, it's simply F over 4.5 m. Moving on to part D, we want to know how much force does block B exert on block C. For that one, I'm going to focus only on the forces acting on block C. And I'm going to write my F equals ma based off of those forces only. So in the x direction, on block C only, I have the force of B on C. And that's going to be equal to the mass here, which is 1.5 m, times the acceleration. And we want to derive this in terms of Fm and fundamental constants. So although this is a proper expression for it, we can't have that acceleration term in there. Luckily, we just found an expression for our acceleration that we can go ahead and substitute in. So I can say F of B on C equals 1.5 m times F over 4.5 m. My m's divide out there actually, and I end up getting that F of B on C is 1/3, because 1.5 over 4.5 is just 1/3 times F. So there's my answer for D. And for E, that final part, we're asking about the force of A on B. So I'm going to set up my forces acting on object B only, okay, to do this. And so it's going to be F of A on B, which is what we're solving for, minus the force of C on B. And that's going to be equal to the mass 2m times my acceleration. I can make a few substitutions here. Okay, I don't know A on B, but I do know that C on B is the same thing as B on C. So I'm going to say minus 1/3 F, just taking that quantity from before. And I can substitute in for the acceleration, F over 4.5 m, okay? And I'm going to go ahead here and solve for A on B. So we have 1/3 F. That's going to be equal to, the masses cancel here, and 2 over 4.5 is really the same as 4 over 9, so 4/9 F. So F of A on B equals 4/9 F plus 1/3 F. That 1/3 is really 3/9, all right, multiplying top and bottom by 3. And so when I add them together, I get that F of A on B is equal to 7/9 F. And there we have my answer for part E. Moving on to the next one here, I'm going to start once again by setting up a free body diagram showing the forces on each object. You can, of course, always treat this as a system, okay? That method works just as well, but I'm going to do the individual one for this particular problem. So on M1, we have the normal force and the force of gravity. All right, we also have a tension force pulling it to the right, which ultimately is leading to it accelerating to the right when this system is released. It's a frictionless surface, so the only force we have there is that force of tension going to the right. For object 2, that hanging mass, we have the force of gravity going down. Notice I called the two forces of gravity two different things because they don't necessarily have the same mass. And that one has the force of tension going up. my acceleration is going to be going down in that situation. So I'm going to go ahead and set up my F equals ma for each object here. For m1, I really only care about the forces in the x direction. So I can say Ft equals m1 times that x acceleration. Can't really do much more with that equation as of now. For m2, when I go ahead and set that one up, I'm going to make down be the positive direction for this case. So I'm going to say Fg2 minus Ft equals m2a. And again, I like doing that. Whenever we're doing these problems, I always make the direction of the acceleration be positive. And so there's my equation for that one. I'm going to go ahead and add these two equations here. And what I end up getting is the FTs are going to cancel out. And I get Fg2 is equal to m1 plus m2 times a. And that's what I always should get. The force holding the system together should cancel out. And then I should just be left with the total mass of the system, m1 plus m2, times my acceleration. Fg2, that's simply m2 times g, so I can make that substitution in there. And what I'm left with then, solving for my acceleration, is m2g over m1 plus m2. And there we have an expression for my acceleration. So that's for situation A. Situation B is actually a completely new situation. So I'm going to go back and start with my free body diagrams because now we have friction and now we're keeping the boxes at rest. So for box 1 in part B, we still have the normal and the force of gravity. And we still have that force of tension going to the right, but now we have a force of friction going back to the left, and we're not moving, so our acceleration is 0. For M2, we have the force of tension going up, we have the force of gravity still going down, and also this one has an acceleration of 0 because they're connected. So setting up my F equals ma, for this one I'm actually going to have to do both max and ma. So in the x direction I have Ft minus Ff going to be equal to 0. So that means that Ft equals my force of friction. And I can make a substitution here that Ff equals mu s times my normal force. And the reason is we want the minimum coefficient of static friction. That indicates that we're going to use all of that force that we have. So in this case, we can make the assumption that friction is at a maximum, and we can make that substitution. So I know that my tension is simply going to be mu s times my normal force. Okay? So I'm going to come back to that equation in a second. Let's think about what my normal force would be. Well, in the y direction, if I think about the forces acting on box 1 here still, so I'll worry about box 2 in a second, we're going to have Fn minus Fg1, and that's going to be equal to 0 because it's not accelerating. So Fn equals Fg1, which is equal to m1g. So there's an expression for my normal force. And now I can go ahead and move over to box 2. Sum of the forces in the y equals may. So I have Ft going up on it minus Fg2. I don't really have to worry about the direction of the acceleration here because I have none. So it really doesn't matter which one's positive, which one's negative. So I can say Ft is equal to Fg2, and substituting in for the force of gravity here as well, Ft is m2g. So right now, I want to find my coefficient of friction, but I have a lot of things in this equation that I don't know. However, if I notice, I just found an expression for the normal force. I just found an expression for the force of tension, so I can go ahead and make those substitutions. So I can say m2g, that's the force of tension, equals mu s times m1g. The g's will divide out. I can divide both sides by m, and I end up getting that m2 divided by m1 equals mu s. Moving on to this next one here, we have an Atwood machine. Two boxes suspended from a pulley system, which is a classic example of a multi-body problem. And so we want to find the acceleration of the system here. So I'm going to start by drawing a free body diagram showing the forces on each object. So on object B on the left side there, we're going to have the force of tension and the force of gravity acting on B. This is once it's released, so it's going to be accelerating up. It's no longer going to be in contact with the floor. I realize that initially it is, but as soon as it's released, it won't be. It's going to start accelerating up, so we're just going to have tension and the force of gravity acting on B. On box A, we're going to have the force of gravity on A, and we're also going to have that tension there, all right? Same tension in both situations, and box A is going to be accelerating down. We're going to go ahead and set up the sum of the forces in the y direction on each of these objects. So on box B, I'm going to have Ft minus Fgb equals mb, mass of box B, times A. Okay, and on box A, it's going to be Fga minus Ft. And I'm doing that because I want the direction of the acceleration to be the positive direction. I always do that. I think it makes the problem work out a little bit nicer, as you'll see in a second. All right, so that's going to be equal to ma times the acceleration. I can substitute in for the force of gravity in both cases. So this is going to be mb times g equals mb times a. And in this case, it's going to be ma times g minus ft equals ma times a. I'm going to go ahead and add these two equations here. And what's going to end up happening, as it always should, is the force connecting the two objects, which in this case is ft. That's going to cancel out. And we're going to be left with the total mass of the system. So when I add those two, I get mag minus mbg equals the total mass, ma plus mb, times my acceleration. Okay, and I can go ahead then and solve for that acceleration by dividing both sides by ma plus mb. So I'm left with mag minus mbg all over ma plus mb. Okay, and that's going to be equal to my acceleration. You will sometimes see this rewritten with the g on top factored out, so you might see it as ma minus mb over ma plus mb all times the quantity g. So that would be another way of putting it. Each one's acceptable. For this next one here, we have a situation where there's a block on an incline with friction, so we do have to account for friction in this situation. And it's connected to a hanging mass with a mass of m. And we want to know what is the greatest and least amount of mass that we can put on the end here while still keeping the system at rest. So as always, we're going to start with the free body diagram for both the mass on the incline and the hanging mass. So for the object on the incline, we have the normal force and the force of gravity. Of course, we're going to break that force of gravity into its x and y components here, fg cosine theta and fg sine of theta. We're also going to have the force of tension from that rope, all right? And we're going to have a frictional force. But think for a second about what we're trying to find here. For this first part, we want to know the maximum hanging mass that we can put on the end of here. So the most amount of mass before the system starts to move. So if we have that situation, if we have the greatest possible amount of mass on the end here, that means that this block is actually in danger of sliding up the incline. So our frictional force is going to be going down. That's going to give us the greatest possible mass that we can place on that rope while still keeping the block on the incline at rest. So that's our free body diagram for the block on the incline. For the hanging mass, we have tension going up and, of course, the force of gravity going down on that smaller mass. In the x direction, our forces are going to be Fg sine of theta plus FF, they're going in the same direction. I'm saying that this is the positive, although you could obviously switch it. And up the incline is the negative. So minus the force of tension. And that's going to be equal to 0 because we are keeping our object at rest here. In the y direction, it's going to be Fn minus Fg cosine of theta, and that also equals 0. So, solving this equation, I get that the normal force is going to be equal to Fg, so I'm going to substitute in mg, and we're using big M because that's the mass of our block, times cosine of theta. On the x side, same thing, I can plug in mg for that force of gravity. And for the force of friction, I'm going to say it's mu s times my normal force minus Ft equals 0. Now, keep in mind that I can make this substitution here, mu s times my normal force, because we have the most amount of mass on the end of that before it begins to slide. So, static friction, and that's what we're dealing with here, static friction will be at a maximum in this situation. I'm going to make a substitution here for normal force. All right, so my equation becomes big mg times sine of theta plus mu times big mg cosine of theta. And I changed it just to mu because that's what we're given here is the coefficient of friction is just mu. It is still a static coefficient of friction though. Minus Ft equals 0. So there's my one equation. All right. My other equation for the hanging object, we only are going to do the forces in the y direction because it only has vertical forces. So it's just going to be Ft minus Fg equals 0. So Ft equals the force of gravity, which I'm going to substitute in mg for. So there's my second equation. I can bring these two together, and ultimately we're solving for this m here. Okay, so I'm going to substitute in that Ft into that equation, so I get mg sine of theta plus mu mg cosine of theta minus little mg equals 0. The g's all divide out here, and I solve for m, and I get m sine of theta plus mu m cosine of theta equals little m. If I want to do a little simplifying here, I can factor out that big M, and I get big M times sine of theta plus mu cosine of theta equals little m. Either one's acceptable, though you don't necessarily have to get into that simplest form. So that's what we have for this situation where we have the maximum hanging mass acting on our system. All right. Let's now think about what happens when it's the minimum hanging mass. Okay, just barely enough mass here on the end of our rope to keep this object from sliding. In that case, it's in danger of sliding down the incline, not up the incline, right? You can imagine if there was no mass here, this block, assuming the angle is steep enough, could slide down the incline. So I'm going to leave my forces acting on the hanging mass intact because none of those change. What really changes is just this force of friction here. So really the only thing that's different, I still have the exact same forces acting on my object. The only thing that changes is now I have a force of friction going up the incline. Because if I'm thinking about that minimum mass that we can put over here, my object on the incline is in danger of sliding down the incline, not up it. So my force of friction is going to be going up the incline, opposing the direction that it wants to slide. So we can go ahead and set up max and may once again for this situation. So in the x direction, I still have that Fg sine of theta. Now it's going to be minus Ff and minus Ft equals 0. In the y, it actually hasn't changed at all. It's still Fn minus Fg cosine theta equals 0, which means that my normal force is equal to Fg, or big mg, times cosine of theta. Again, just making that substitution for the force of gravity. Over on my x side, I can plug in big mg for the force of gravity. I can substitute in mu s times my normal force for the force of friction, because once again, our force of static friction is at a maximum, okay? It's providing the most force up the incline to keep this object at rest. And then I have Ft, and it's equal to 0. I can move this Fn over, okay? And so what I end up getting then is big mg sine of theta minus mu times mg cosine of theta. And again, I'm just plugging in for the coefficient of friction that I was given up top there, minus Ft equals 0. Plugging in that Ft, we end up with big mg sine theta minus mu times big mg cosine theta minus little mg equals 0. G's cancel out here, and I can go ahead and solve for little m. And so I end up getting m sine of theta minus mu m cosine of theta equals little m. Just like last time, I can substitute or factor out that m and simplify it, although this expression is perfectly okay as well. If I do factor it out, though, I'm left with m times the quantity sine theta minus mu cosine theta equals little m. So the only thing that really changed was this sign right here. That's the key difference. And that comes from, is friction going up the incline or is friction going down the incline? Next problem here, we're once again going to set up a free body diagram for each of the objects here, the m, the 2m, and the 3m. So let's go ahead and do that. For the one hanging mass, we have the force of gravity, I'll call it Fg1, and the force of tension going up. For the mass on the table, we're going to have a normal force, we're going to have a force of gravity, we're going to have two ropes actually acting on this, all right, one going to the left, connected to the 3m, and one going to the right, connected to the 2m. I do want to distinguish between these two, so I'm going to call that rope on the left-hand side, rope A, and the rope on the right-hand side, rope B. So we'll make the force between the m and the 2m, FTA, and the force between the 2m and the 3m will make FTB. Okay? I'm also going to have friction, so let me think for a second about the direction of my acceleration. This mass here is greater on the right-hand side, so that means this system is going to be moving that way. So this mass is accelerating up, this mass is accelerating to the right, and the 3m will be accelerating down. So that means that my frictional force on the block sitting on the table is going to the left. And then we have the forces acting on the 3m. We have FTB, the force of tension in that rope between 2m and 3m, and FG. And I should call this FG2 and FG3. Now that I have that, I'm going to set up max and may, or only may in the case of the two hanging masses, for each of these objects. So for block M, we have FTA going up minus FG1 going down. That's equal to MA. I'm making the direction of the acceleration be the positive direction. And I can substitute in for FG1. All right, so it's just going to be mg, and that's equal to ma. So there is my first equation for the block with a mass of m. For the 2m, I need to set up both max and may. So in the x direction, I have ftb minus fta minus ff, and that's equal to 2ma. Okay, again, making the direction of the acceleration be the positive one. All right, and in the y, it's going to be Fn minus Fg2 equals 0, because that block's only accelerating to the right, not accelerating vertically. So that means my normal force equals my force of gravity, which in this case is 2mg, just mass times g. So there's my y equation, and I can now use that normal force to substitute in for my x equation, because I can say my force of friction is mu times Fn. I'm given that coefficient of friction here as just mu, so I'm going to leave it as that. It is a kinetic coefficient, though. And so I end up with FTB minus FTA minus mu times 2mg is equal to 2ma. So there's my second equation. And my final equation here, for the other hanging one, we're going to set up my may only because there's only y forces for that one. And so I get Fg3 minus Ftb equals 3ma. Again, making the direction of the acceleration be positive. I'll substitute in for Fg3 as just 3mg minus Ftb equals 3ma. I'm now going to take these three equations that I've gotten here for each of my objects, and we're going to add them up. So when I go and add up those equations, I find that the FTAs go away, right, because we have FTA minus FTA, as do the FTBs, which makes sense because those are forces that are just holding our system together, so they should cancel out in our final expression. And what I'm left with is 3mg minus mu times 2mg minus mg equals ma plus 2ma plus 3ma, or 6ma. And so we see the force holding them together goes away, and we're left with the total mass times our acceleration. We can cancel out the m that's in every single term here, okay, because it is in every single term. Do a little simplifying, and so we have 3g minus g, so it's really just 2g minus 2 mu g equals 6a. Okay, if we're solving for our acceleration, it really becomes 2g minus 2 mu g all over 6. We could do some algebra to rearrange this a little bit, or you could just leave it like that. That's perfectly acceptable as an answer.